Welcome back after the lunch session. In the first session, we had a short description on the wind energy and wind turbine. Now coming back to the second session of today, it will be on wind energy fundamentals. Thank you. Thanks.
So, afternoon, everybody. So this is a 2-hour session. So we'll have a short break in the middle. And though I had given a break actually just by mistake last time because it was really 1.5 hours. We didn't need the back. But anyway, worked out well eventually. So we've seen various aspects of wind energy and turbines. And key issues that we'll be discussing in the next few days. And we start now with some of the fundamentals of wind energy. So, first of all, let's again revisit the principal subsystems of a wind turbine. And this is something we have already discussed broadly about different elements we have, but without going into much of a detail of any of those. So I have mentioned certain things following the questions I answered. So if you recall, we had a discussion on upwind and downwind turbine. So I didn't say exactly what it meant and so on. So the first concept of a modern wind turbine, the horizontal axis wind turbine, relates to the design of the wind turbine depending upon the direction. So the left-hand side, we have a wind turbine, and here you can see the wind turbine blades are actually facing the direction. So this is actually called an upwind design. Whereas on the right-hand side, you can see that there is a wind turbine, but in this case, the wind direction is actually coming from the back. This is actually downwind turbine. And as we discussed, that if the wind comes from the back, and it's obvious, we don't even need mechanics to say that, the wind actually is being obstructed by the tower. So if that's the case, then obviously all of the wind is not able to pass this freely. And there is actually what is called a deficit of wind created following the obstruction by the tower. So every time a blade passes the tower, it feels that suddenly there is a drop in the air velocity. Now, not necessarily a drop in velocity means a drop in pressure, because we know from Bernoulli's principle that dynamic pressure actually consists of the velocity and the pressure. But you also have these terms which will be a combination of the effect of the velocity and pressure. So therefore, essentially what happens is that there is a wind deficit here, and that causes some kind of a dynamic loading. So then one might ask that if that's the case, why do we at all go for downwind design? Why not we always do an upwind design? Any answer? Because apparently it seems that, oh, actually this is sort of obstructing the flow of wind direction. If I do have a choice, the question is, do I have a choice? If I do have a choice, then I should then go for this upwind design instead of the downwind design. What's the advantage in a downwind design? Because always the wind is coming from this direction and hitting the wind tower, and therefore causing this deficit, obviously, a drop in power, pressure, and so on. But definitely, eventually it will lead to a loss in pressure, in power generation. The point is that if we want to go for downwind design, if you want to go for an upwind design, we need an additional control system. So what happens is that you have two kinds of design. In one case, you can allow the rotor, meaning the nacelle and the blade, to freely move around. So if the wind blows, naturally, it will align itself according to the direction. So it's a free alignment, free yaw. If you have free yaw, that's an advantage because then you don't need control system. So that means obviously the cost of control is not there. And also, if the control doesn't work, you don't have to worry about that. Because if you have a controller, if you're relying on the controller, then if the controller fails, that's a problem. But if you haven't designed, right, for a controller, then you don't have to worry. Just like, the difference between an aircraft and a glider. So in a glider, you have a mechanical control. So you don't have to worry about the failure of the control system. And in an actual aircraft, you've seen what happens if an aircraft controller fails. We have seen it firsthand very recently, actually, right? So therefore, the recent aircraft crash that happened. So means that obviously relying on controller and the cost of controller is what we pay if we have to go for this particular design. So you need then your controller to make sure that you're facing the wind direction. Whereas in this case, you can leave it and it's free to move and align itself. So there's no yaw control there. But that might lead to a downwind design. And that means you can actually have a power deficit, which actually is not good. So that's the main difference between the upwind and downwind design. But with all the modern controls we have these days, most of the wind turbines that we design are upwind design. So really don't have to worry about this. But even then, we have seen that even though it's an upwind design, we cannot actually still have a completely free flow following this obstruction of the tower. So there is going to be a change. Obviously, there's going to be a change in velocity from this end to the other end. And because of the change in, again, apply your Bernoulli's principle to our boundary conditions. So in that case, deficit because of the tower shadow effect. And we saw a simulation in the morning where I showed how the blade was deflecting, just on as a part of the project in seconds. So effectively, we can still have a tower shadow effect, but not so prominent as in this particular case. But really, that's really the difference between the two, upwind and downwind design. What it means. So now going back to the principal subsystems of a horizontal axis wind turbine, you have the rotor, and the rotor, when we say rotor, we mean the blades and the hub. Now, depending upon which area you're focusing, whether it's mechanical or electrical, rotor may mean different things to different group of people. So for an electrical engineer, rotor obviously would mean the generator. Whereas for mechanical engineer and aerodynamicist, the rotor would mean actually the blades hub. So both are actually rotor. One is the slow That's why I would actually like to classify it more as a slow speed or the low speed side of the rotor and high speed side of the rotor. So the low speed side of the rotor is basically the blade and the hub. The high speed side of the rotor is basically the generator. So it's better to clarify what you mean by the rotor. Next is the drivetrain. That's actually the rotating part of the machine in the box here, the nacelle, and that's the vulnerable part because within few months of operation, and there are a lot of figures you can get on the net or several books, will show you how much damage can actually happen on a gearbox. And gearbox actually is the particular mechanical system in a wind turbine that needs replacement for sure for all wind turbines, and maybe 2 to 3 times of the lifetime of wind turbine. By the way, I didn't say that almost all wind turbines are actually designed with a lifespan of 20 years. So the time span of operation of a wind turbine is 20 years. Unlike many other systems, we have longer or maybe shorter lifespan. But typical design lifespan for wind turbine is 20 years. And normally they're under warranty and maintenance for 5 to 7 years. So beyond that, you can renew your maintenance contract with the company that has provided you the wind turbine, or you can choose to have your own operation maintenance or give it to another company. But it's an enormous task because normally the SCADA system here would monitor about 200 parameters actually continuously. So you can imagine the amount of data you're generating. Of those, not everything is that well analyzed, not done in real time. Most of the time, they get the data, goes to a data center, it's sent to another company who is doing an O&M. So, for example, Siemens in Munich, they do the O&M, or sometimes it's actually sent over to another company. So, the wind turbine might be operating in Arnhem, owned by some county council, maintained by Vestas. The data acquisition is done by a company in Finland. They send the data to another company in Bulgaria. So it's very complicated actually, the way it works. But this is how it operates. Sometimes they have their in-house monitoring as well, or analysis of the data, like Siemens, I said, or when Alstom, for example, used to do energy, now they have sold it off to Siemens actually. But they had their own O&M group, and still now they have their own O&M group because they do O&M for a large number of logistics companies for all over the world, for all high-speed tracks and trains and so on. But they used to have O&M done in Paris, in their R&D center. So it's very specialized job, and this is where a lot of people use deep learning and machine learning, and so on these days, trying to see this SHM or PSH, all this kind of things, to see when is the next gearbox replacement needed. So predictive maintenance, proactive maintenance, and all those sort of things. So they acquire the data, they use either historical data to compare, benchmark, or they use different schemes to identify faults and conditions of the system. So basically, if you look at this again, then the rotating part, which is the most vulnerable part, as I said. And in fact, what happens is that normally, if you order a gearbox, you won't get it tomorrow. You have to wait for some time. So what happens is that during that period, you have to wait, and that means you cannot actually connect to the grid. Now, if you are a wind farm operator, and under some regulation, you're by law, by contract, you have to actually produce a certain amount of power and be connected to the grid for a certain period of the time. In fact, quite stringent, in fact. You have to be, because these are rotating machineries, like thermal power plants. So they have inertia, unlike photovoltaics. And therefore, they also provide damping to the power system grid. So it has also that role to play. See, if you disconnect from the grid, then obviously the grid has a loss in inertia, and that actually is not good for the grid also. And if you lose the grid inertia, then that might change your stability, in fact. And in terms of the dynamics of the systems and time scales, we are operating at very different time scales. Like if you're talking about the low speed side, we've seen already that the rotational speed is of the order of seconds. Most of these flexible systems, gearbox and those kind of machineries will show certain defects, which is of the order of, say, kilohertz, 2 megahertz. Generator fall definitely at megahertz. When you go to the grid and you're talking about the power, then you're talking about like definitely megahertz, even multiple scales, superharmonics and so on. And the time scale then essentially is of the order of few microseconds. So like if you look at the grid code would say that you cannot actually allow a dip in voltage of such and such percentage by 20% more than, say, 400 millisecond duration. So that is the time scale we're talking about. So if you have to have a control system in place, then you must identify what's going on within that period and take some action. So that's a very fast scale we are talking about. So the scale varies a lot in terms of the time scale. And then obviously, there's also clutch and brake also in this system, because if you're trying to stop the operation of the wind turbine by reducing the speed of the blade, there are two ways to do it. One is by using some kind of a torque controller. That torque actually comes from the generator. So the generator can produce a counter torque and slow down the speed of rotation here. But also, you can actually apply a mechanical brake like you do in a car and stop the operations as well. That's done for emergency, like emergency shutdown. You have to stop it, so there's no other option. You have to apply a brake. So, yeah, so while I was discussing about this, I mentioned about the time scale of operations and so on. So obviously, we are looking at various different time scales at the two ends. And as I said, that if you're looking for real-time O&M, then you have to act on certain things very quickly. Whereas it's impossible to analyze this 200 data that we collect. Some are more important than others probably, but typically the things that measure are obviously the speed of rotation of the rotor, meaning the blade, but not really from here. They measure the speed of the generator, and then you know the ratio. From there you can find out the speed. The wind speed is definitely measured. The acceleration at the hub and the cell. Bending moments at the root of the wind turbine blades are measured, strain gauges, and so on. Accelerometers are done, put on this for measurement. Torsional oscillations are measured for the drivetrain. For the generator, obviously, you measure the current and the voltage, the frequency, and obviously there are other parameters which are used. Like if you want to do the O&M, then thermal analysis of the lubricant basically is used. Find out how much of suspended solid particles are there, and that will tell you the condition of the gearbox. Because if there's wear and tear, obviously there'll be small particles in the lubricant. So by doing an oil analysis, so oil analysis also gives a lot of information on the reliability of the system. And then based on that, you have to take decisions. And they can be done either real time or can be sent to some data center and then information retrieved passively. We've discussed about the nacelle and the mainframe already, so I won't go into the details, but the turbine is housed here, and there are bed plates as well, which is supporting all these devices. Now, these bed plates are also very vulnerable. They are also damaged quite frequently, but not as much as the gearbox. So in terms of damage, the gearbox is the most vulnerable, definitely needs replacement from time to time. But again, from the downtime point of view, I mean, there is a downtime. We were discussing about downtime and the requirement to actually be connected to the grid, but the downtime is not very high. Whereas if you have, for example, a blade damaged, that doesn't happen that often. But if it does get damaged, then the cost is enormous for that, because a replacement of the blade could be a huge amount of time and effort and so on. And obviously, replacing is not easy. whereas a gearbox is much easily replaced than a conventional blade. So damage in a blade is less frequent, but the effect is far more significant. Damage in gearbox is more frequent, but the effect is not that significant. So obviously, we need to look at both, but in different ways actually. So a regular condition monitoring of the gearbox would tell you when you need to order the next gearbox, because you don't want to wait till the next gearbox is required or the gearbox gets fully damaged, because you know the gearbox will need replacement. It will be damaged. The question is when exactly. Whereas in the case of the blade, you really don't want the blade to get damaged actually. So you really don't want the replacement, and therefore the main thing here is to see and really make sure that we don't need a blade actually. And in case of gearbox, you're saying, well, find out when do we need the next gearbox. So the different approaches there. And the same applies to tower, because rarely towers are never damaged actually. They're fairly stable structures. Once it happened, the whole thing got toppled over, but I think that's because of a problem with not the foundation here, it was the offshore one, so it was actually a floating turbine near shore. So there's a problem with probably the connection between the top slice and top splicing and the tower. So there is a, there's a sort of cylindrical foundation which is called a monopile, like piles in buildings, but they use much bigger steel cylindrical shells. So they're essentially shells. And then on the top of the shell, there is a splicing intermediate element put in. And that is done for two reasons: to connect the tower to the foundation, but also to take care of any misalignment. So, if there's an eccentricity, then that will induce a lot of movement. So to make sure that you have a stable base, so you have the foundation, and then there is an intermediate splicing used to connect the top tower at this foundation. So I think the problem was there. And normally the failure happens at connections and stiffening systems in towers. Like tower is not, again, an integral single design of the whole tower. It's made of, again, splices. And so locally where the joint is there, so the connections fail actually. So the reliability of the connections are poor. As in the case of offshore structures, the structures, they are overall more reliable, but connections are not. In this case, obviously, the drivetrain definitely is subject to a lot of stress. And then machine and controls. So obviously, one is a generator torque controller, as I said, is needed to control the speed of rotation. There's a pitch control we have seen this morning, which controls the angle of the blade, which is effectively controlling the load acting on the blade, but also used to control the efficiency. Because depending on the angle of attack, your lift and drag will change. So the aerodynamic load will change, but that will also change the torque. So the load is not just a load, but the torque is actually the generating power, because torque multiplied by your rotational speed gives you the power. So obviously, the torque is also contributing to power generation. So you need to control that as well. So therefore, there is also a pitch controller and torque controller here. And then you have a yaw controller to control the movement of the cell at the top, properly angle or align it. And then you have the power electronic controller, control the quality of the power. So what we generate essentially is a current and a voltage. And they have some specifications, like the voltage has to be 220 volt, the current has to be like a certain ampere, and the frequency of oscillation has to be like 50 hertz. So all these are basically required for proper clean power generation. So in this clean, I don't mean the renewable clean, but it means that the power is clean. Because if you don't have clean power, what's going to happen is that if you feed it to the grid, if there's too much of pollution in the grid, this pollution is not the pollution again. We mean in the context of the normal pollution. But that will pollute the grid and the system. And we are using a lot of electronic devices these days. Yeah. So all your audiovisual system, my laptop, your tablets or other equipment you have, they will be damaged eventually. So the life of those systems will be affected. That's actually very difficult to accept. You don't want really your laptop to. We don't think about those these days anymore because the power quality is so good. But those who recall, and even for critical equipments now, like in hospitals and some other places, they use something called UPS or uninterrupted power supply. That's really what it's doing, is giving you a clean power, filtering the power. Make sure that it's of a certain specification. So, therefore, you really don't want your equipment or electronic system to be damaged because they are very expensive as well. So that's done by the electronic controllers, and then you have also the generator controllers to control the generator, connect to the grid, and so on. So therefore, we put all these things also under the balance of electrical systems, including cables, switchgear, transfer, and power electronics. Normally, they're kept at the ground level, not at the cell, because power electronics is at the cell, but these are really at the ground level. We have the switchgear, the transfer, and the cables, and so on. So that's sort of a complete picture of a wind turbine on the on balance. You see that what you have from the aerodynamic side, and then where it goes on the electrical side. So I think this now basically allows us to go a bit more detail in each of these components to find out about these. So I mentioned this morning the blades and the number of blades. So we have already discussed about the rotor configuration in terms of spelling correction here. It's quite obvious, downwind and upwind. But number of blades, usually 2 or 3, and 2 is preferred because 3 is preferred because if you have 3 blades, then if you add the vertical components and the horizontal components, then what happens is that there's no net horizontal force acting. And beyond 3, the total mass at the top of the tower increases. So your design cost increases, but the efficiency in terms of power that we get is not that much. We'll see that later. So that's why 3 is sort of optimal. Now, blade materials are usually made of composites, fiber reinforced composites in laminate form. But companies are also now trying to make, because if you have laminates, then delamination is a problem. So they're trying to make it with a single shot design, meaning that instead of laminates, you have everything made together. So delamination can be avoided in that case. So this is a particular manufacturing procedure they're using for blades. The profile kind of resembles the airfoils. So you have the NACA profiles, and typically those are also used here. But mainly the characteristics which guide the design of a blade is the power coefficient, and essentially it means the lift and the drag. In terms of the power control, I mean, there are 2 types of control possible. One is called stall design. The other one is called pitch control. Now, aerodynamic control, which is also called the stall. Again, if you recall this morning, we're talking about stall induced vibration. We also mentioned about machines, which were basically stall-based machines. They are mainly passive designs based on aerodynamics, so that we ensure that more or less the coefficient of lift is constant throughout the length of the leg. And that we do by some aerodynamic design. Now, I just draw a wind turbine blade here. So we have seen this morning that in 2D, the profile looks something like this. Okay, let me draw the wind turbine first. So this is the core of the cell, and these are the three blades. Power is something like this over here. Okay, so this is rotating, speed of omega. And if you take a cross section here, in 2D, the airfoil looks something like this. So this is the cross section here. And this is the nose of the leading edge. That means this is where the wind comes and hits the blade. And this is the trailing edge. So typically, wind comes like this and then goes out like this. And if there's no detachment, eventually it margins like this. So now, the shape of this particular cross section determines the load coefficients like the lift and the drag and power generated and so on. And that is effectively governed by, if you look at the wind velocity v coming here, and this is the angle say. So the angle at which this velocity hits, and this line from here to here, basically is called the, this is the chord length, C. And by changing this angle, what happens is that this flow around this shape of airfoil is called an airfoil. So this flow is affected by this angle. And at certain angle, what happens is that you can see that flow is kind of following the shape of this airfoil. But under certain circumstances, it may so happen also that if you have something like this, then the flow comes here, and then instead of reattaching, it gets detached. So this is called a flow separation. Here there is no separation, that's fine. But on the top, the flow comes in, hits this nose of the airfoil, and then tries to follow this, but then at some point gets detached. So meaning that there is actually a region over here where this detachment of flow. Now obviously here then you have something like circular motions, which is sort of a wake. This is actually called a wake, which is caused at the trailing edge. This is called a flow separation, detachment of the boundary layer. So because when the wind blows, there's a small thin layer which gets attached to the surface. This viscous layer, but then that actually gets detached. Detachment causes some kind of wake, not really turbulence, but eventually may lead to turbulence. So this is where some energy dissipation may take place. This wake effectively means that if you have this velocity here, there is a portion where you have some pressure, which is actually lower than pressure. So effectively, it has a structure of flow like this. And when this happens, what happens is the lift actually then decreases. So here, The lift actually is caused because of the pressure difference between the top and the bottom. There's a pressure here, there's a pressure here. And the pressure normally at the top is lower. So pressure at the top, at the upper face, and pressure at the lower face, PL. And pressure at the upper face is actually less than pressure at the lower face. And that is the reason why the lift happens, because it pushes up. Whereas in this case, because of this phenomenon, this lift doesn't happen. So you don't have this kind of situation. And that means this gets stalled. It doesn't lift anything. So this basically is caused due to the stalling of the device. Now, to avoid the stall, we need to make sure that the angle of attack is of a certain value, because the stalling depends upon what angle it's hitting. Now, if you look at this blade again, and let's look at this particular blade, and so because the wind turbine is rotating like this with the speed of capital omega, can you see from the back or not? Do you want to come forward? There's a lot of space here. I think all of you should come forward, because otherwise you won't be able to see the whole. So if the radius is r, then effectively you have a velocity of omega times r, right? So if you take a cross section at the tip, like I have that there, so there are two velocities there. One is the velocity of the wind, and the other one is the velocity of the rotation due to the blade here. And there's a relative velocity as a combination of the two as well, but there's a velocity which is omega r, and then there is a velocity at which it is hitting this. So this is v, and this is, say, rotating with a velocity of something like omega r. So this is v, this is omega r. So the net velocity then is the sum of the two. Okay? Or actually, this is what is felt by the blade, and this is omega r is the rotational velocity of the blade. So that means if this is the final velocity, then the component of the velocity is something like this. So this one and this one gives you the resultant velocity. So effectively, two velocities are acting here. One is omega r, the other one is the velocity of the wind. Now, the velocity of the wind is not changing, assuming more or less uniform over the rotor plane. What is changing is omega r. And omega r is dependent on the position on the blade. Because if you're at a distance of r, then this is going to be omega times small r. And what happens at the hub then? What is the value of r? 0. So at hub, you have r equal to 0. And that means that component is completely absent. So there is actually a change in the net angle of attack from this end to the hub. Now, if we want to get the same kind of coefficient of lift for generating power along the whole blade, because at the moment what's happening near the hub, it's not very effective because omega is 0, or not, sorry, not omega is 0, but the effect of omega times r is 0. So therefore, it's changing a lot. But say if we change the angle of the blade itself, so this is my airfoil. At the tip, it's like this. But let me now twist the blade actually. So that's why the blade is given what's called a pre-twist. The blade is not just a straight blade, but to make sure that we still have some angle of attack near the hub, we twist it. So at this point, we have a cross section like this, but as we go along the blade, then this changing this particular airfoil section changes the angle. So here we have it like this, but if you move somewhere here, then effectively it is something like this. So now if you have the V like this, even though there is no omega times r, but net velocity actually is still the same because the angle of attack is the same. We are twisting the blade to make sure that the angle of attack is actually more or less maintained along the blade. So this is an aerodynamic design, and that's why it's called an aerodynamic control. And this is the stall design of blades. So stall controlled wind turbines were used previously, and this is where the problem of stalling happened. And once it's stalled, so obviously if it's stalling, then you don't have lift anymore. And then what happens is pressure takes because of this. Now, I told you that the pressure here is lower than the pressure here, and you accept it. Why is that? I don't know if I have explanation later, but I think I have it. So keep this question in your mind, that that I have, and there are actually more than one justification. So there are two different theories. But who tells you the pressure is higher at the top and lower at the bottom? Sorry, opposite. Lower at the top and higher at the bottom. Well, it has to be, obviously, because otherwise we won't get any lift. That's true. But I haven't told you anything to really say. Yeah.
Actually, one theory was that, actually I studied a little bit. Actually, one theory was that two particles you start by front point, they will meet at the end point at the same time.
Yeah.
I think that one theory was there.
And so what happens?
And it was never get that approval. So new one theory came that actually I followed.
Yeah,
No,
the velocity will be higher at that point because it have to move the longer distance.
Yeah. Velocity will be higher. And
so
then
because of Bernoulli's principle or something.
So yes, I have in the slide. So that's one of the theory. I think we'll go in detail. But essentially, what happens is that, and this is the assumption that this flow sticks to the surface. And if it does, then you can see that because of the shape, this distance is actually greater than this distance here. That means if the flow, then the flow at the top has to traverse a longer path compared to the flow at the bottom. And assuming that there's no separation taking place, that's why this is different from this. I said this doesn't happen. Okay. Then because it traverses a longer path, but at the same time, because they have to meet at the same point, because of no separation, that means the velocity here will have to be higher than this point, this part of the bottom. So if the velocity is higher, then if you apply Bernoulli's principle, then you have the term, which is the pressure gradient, but V square over G, then obviously where you have a higher velocity, the pressure has to go down. So the pressure is lower here, pressure is higher at the bottom, and that actually is causing differential pressure. But there is actually another theory, which is, in fact, I think this is sort of a more hand-waving argument, which I just told you. But really, if you see that, if you look at the curvature, then this is basically curved and this is curved. So the flow which was coming here straight now has got curved at the top and also curved at the bottom. So because this is also curved, this part is curved, this part is curved as well. So the flow has got curved, and we know that if anything gets curved, then it has to have something called a centripetal acceleration activity. So that means if you have a curvature in the flow, there must be a force which is acting like this, make this up, and which is your centripetal acceleration. That is normally given by V square over R. So essentially, it is corresponding to this curvature, which is basically R, and the velocity square. And that force will have to be counteracted, because if that's a force acting, obviously, and bending the whole thing, and then obviously that has to be, and that's acting on this body here as a reaction. So now, if this body is being acted upon by that force, obviously this whole thing is curved, the flow is curved, but then this body is not moving away because it's static in a particular position. There must be a counteracting force on the body as well, right? So effectively, what happens is that the pressure difference is basically nullifying the centripetal force required to make the fluid flow in that curved form. So the effect of this presence of the body is that it's making this flow pass like this. That means that force is acting on the fluid, but the reaction is then what acting on the this particular body, and that is because of the pressure difference. So this is another sort of explanation why it happens. But the other one, as we discussed, is as I said, based on the Bernoulli's principle and why it is takes a longer duration to travel. So in fact, that one is a more favored one compared to the centrifugal or centripetal acceleration curvature. But these are the two theories which says that why you have a lift, or the explanation why you have a lift. You know why you have a lift, because you have a force coming, like if you have a velocity coming like this, and it gets stopped by this airfoil, then there must be a force generated, and that force generated has two components, one long and one normal. So the force which is perpendicular is the lift force, in the direction is the drag, and obviously this is the net force then. And because it's 2D, so obviously this force also has to have a moment along with this. And the distance where it happens is basically 0. I think I have this in my lecture notes as well at some point. So this is basically the stall control design. So not this part which I explained here, but the fact that as we move along the blade, R is getting reduced. So at the hub it's 0. So obviously the net effect of omega R is not there, but make sure that we have the same angle of attack so that we can have enough lift along the blade. We pre-twist the blade, and this twist then effectively is causing the angle of attack, and that's actually a stall design, which is sort of passive design. So the first control is actually an aerodynamic control, which is a passive control, and then the second one is called a pitch control, where we change the angle of attack by using an actuator at the hub and rotating the whole blade. And by that, we can also change the angle of attack. So one way is to use the pre-twist, the other one is to change the blade angle altogether and change that. So that's actually the variable pitch control. Now, you can have individual control or you can have collective control. So you can change the blade pitch angles for all the 3 blades together, or you can individually change for each of the blades. That will lead to individual as well. We had also discussed about the fixed or variable rotor speed, free and active yaw control, gearbox and direct drive generator. Direct drive machines are mainly and that's because you can almost change the speed to a speed which is same as the speed that you want to generate. So all the permanent magnet machines or generators, they have this fixed speed machines, but they are also close enough to the speed that you want to generate. And the way they do it is by changing the number of poles and windings on the generator. That actually has an impact on the frequency of generated current and voltage. So depending upon the number of polarities, so that many number of times it will be crossing 0. That will change. It's essential. And then we have also had a discussion of the synchronous and induction generator in small units. So So I think this is something that we have already discussed again. And we had discussed about the importance of the blades, the performances, and why we need 3-bladed turbines. So we have just now discussed about the fixed blade pitch with stall control, and these are suitable for intermediate size. As the wind turbines grow bigger, you might have a chance of getting that stall-induced vibration. That's why for increased size, the pitch control is used. The materials we said are mainly GRPs, but wood epoxy laminates and carbon fibers are also used for it. So this is something in relation to the rotors. Just one thing is, I did say that 3-bladed is important, and that's really optimal because by increasing the number of blades, your total mass, the design cost increases without much improvement in the power efficiency. Also, I mentioned about the net force, and in terms of gravity, if you see, so if you take the 3 blades and take the self weight of the 3 blades, and with the 3 loads, we can see that there will be 2 components. One essentially axial, the other one the lateral. So all the lateral components are actually nullified. Even there is an eccentricity, that will be actually nullified. So that's one of the advantages of having a 3-bladed turbine. So maybe we'll continue for another 3-4 minutes and then take a break. Right.
Pre-test.
Sorry.
So when you give the pre-test, are we actually changing the angle of attack, or are we making it as constant? Because when you give pre-test, phase stream velocity direction doesn't change.
No.
So you said to make constant lift.
Yeah. So if
are we changing the angle of attack, or is it constant?
Yeah, we are changing the angle of attack, because if you change the twist of the blade, then the relative angle of attack gets changed. So the free stream velocity is coming in a certain direction. That's not changing. But because now we have changed the twist of the blade, the effective angle of attack has changed. So I think we have discussed about the rotating parts as well, in terms of the low speed shaft, the rotor side gearbox, and the high speed shaft on the generator side, the supporting bearings, couplings, brakes, and rotating parts of the generator. In terms of gearbox, there are 2 types of gearbox. One is a parallel shaft, and the other one is a planetary gearbox, which is used for larger machines. And in case of a wind turbine where heavy gear ratios are necessary, obviously you can go for multi-stage parallel shaft as well, and that's normally done. You can also have planetary gearbox systems. I told you that maybe I'll provide you with some supplemental material on gearbox. So I'll probably give it to you tomorrow morning. Obviously, the loading here is very complicated in the sense that the wind is a fluctuating load, and the dynamics of large load subjected to wind obviously has some complications in terms of what or how they interact, depending upon the blade which is rotating in a field of turbulence. And obviously, it will generate, first of all, periodic loading because of scanning of the wind shear, which is varying with height as well. So that's the first thing. But also you have turbulence, so that will also have some random loading. But this random loading is also very complicated. It's not like normal wind turbine, not like other random forcing that we see. And we'll see that in this case, the random loading gets actually modified because of the rotational planes. It's called rotational sample spectrum. So we'll discuss that when we talk about the turbulence. In terms of the generator, We discussed about the induction or synchronous machines. I said that induction machines are becoming more popular because they're rugged, inexpensive, easy to connect to the networks, and obviously with variable speed turbines, there's less wear and tear and more efficiency. But people are going for now more fixed speed machines, or something what's called a squirrel cage induction generator, where you can actually fix up the speed, but then you don't worry, because if you generate a certain power with a certain frequency which is not matching what you want, you convert the whole thing into a DC. But if the frequency is low enough, then conversion is not a problem, or electronics cost is not high. And then once you have converted AC to DC, you again use a converter to make the DC back to AC. So use the rectifier from AC to DC, and then DC to AC back for transmission. That's why people are not actually worried about variable speed machines. They're using more fixed speed and squirrel cage induction generators, particularly for offshore case where maintenance is an issue. And then in terms of hardware, obviously, for the variable speed machines and for power electronics component, we need suitable converters, and then control flow those are also required. So these are mainly the electronics part of it, which are controlling the generator torque, controlling the power electronics, and the speed of the turbines. Nacelle and yaw system, obviously housing the wind turbine, machine bed plates, and so on. And among other things, nacelle is required for protection against the external weather. And again, the nacelle is made of, again, some composite material and lightweight. And it works better there because obviously the cell is not subject to any significant dynamic loading capacities. Then you have the yaw system, and you can have active yaw system, which contains motors with the drive pinion gear against pulley gear attached to the yaw bearing. Sensors are usually implemented on nacelle, and brakes are there for yaw bearings. And in case of a downwind machine, the yaw is free, as I said. Move. The tower is normally a cylindrical tower and freestanding, and you can have lattice or concrete tower as well, or composite towers. For small turbines, you can also have guide towers that are connected by cables and stable cables. Typically, the tower height is 1 to 1.5 times the rotor diameter. The possibility of tower rotor vibration getting coupled, which we have explained in theory and in concept, we'll see how this coupling happens when we derive some equations, maybe not tomorrow, but the after, when we look into the structural dynamics modeling, how the gyroscopic stiffening gets connected, how the damping actually gets affected. So that's where you see that because of this coupling of the mass, we get a negative damping there. Damping. And the velocity terms comes because of the coupling. So not just there's an inertial coupling, but there's also coupling in the velocity terms as well. And then for downwind rotors, effect of tower shadow is very complex and obviously can cause power fluctuation, but also noise generation. And finally, the controls are very important. I don't have to say, I mean, we've been talking about this all along. So you have sensors to measure the speed, position, temperature, flow, current, all those things. And controllers could be either mechanical, electrical. Mechanical controllers like the viscous dampers are there to control the yaw damping. There are also other sort of dampers to control the damping in case of actuation with the pitch as well. And then there are power amplifiers, switch, hydraulic pumps, valves, actuators, motors, pistons, magnets, and solenoids. Pretty much everything you can think of, everything is there inside the engine. And finally, what's our aim? Our aim is to put an upper bound on the top and power experienced by the drive train. So basically what we want to do is maximize the torque that we produce with the constraint that the power experienced by the drivetrain will have to be limited. So that's the first thing. We want to maximize the fatigue life of the rotor drivetrain and the pump. And finally, we want to also maximize the energy function. So these are the three aims we have in designing the whole system. Okay. So and finally, I think this is the last slide in terms of the subsystems in the description. The electrical systems, which we won't go into detail, but obviously the cables, switchgear, transformer, as you can see, any power system and power electronics converters, because as I said, the power quality is very important. The off-pitch motors and then interconnection with the network. So maybe I'll stop here. So we just covered 1 hour. So let's take a short break of say 5 minutes, not a very long one, because I want to cover the whole thing within the time frame today. So short break of 5 minutes. Do you want to have some questions prior to that? Or you want to have the question answer at the end? Because then I'll keep a 10-minute slot at the end where we can discuss things. Okay. So we'll see you in 5 minutes.
we are coming back to our session. Thank you.
Thanks. So we are running a bit late, actually. So that's the bad news. The good news is I think we've cleared out of the basic concepts. So the next few slides are going to be more mathematical, more technical in that sense. But then, because we have understood a lot of the phenomena, it won't take very long. So I'll scan through those very quickly because we need to finish a significant part of it. So let's now look at the power generation from a wind turbine. So this is basically a curve which tells you how much power is generated as a function of wind speed. Now, so this particular speed is called the cut-in speed. And then you look at the curve, it's approximately a cubic curve. See again, do the derivation. With a peak somewhere here. And that's actually called the rated power. And that's somewhere 15, 16, 17 meters per second. And then beyond 20 per meter per second, there's no power generated. And you have to stop the power generation. This point is called the cutout point. So the rated power is determined by the generator rating. The cut-in speed is mainly determined by the overall machine specifications. And then the cutout speed is beyond which no power is generated or allowed to be generated. And that's determined by what is actually acceptable in terms of operation of the machinery. So safe operation is basically the guiding criteria for this. And these are the three definitions. The minimum wind speed at which the machine will deliver useful power is called the cut-in speed. The rated speed is at which it gives the highest or maximum power, and it's corresponding to electrical generator, obviously. And then the third one is cutout speed, which is where it stops, essentially the maximum speed. The turbine is allowed to deliver power. It's mainly governed by the design and safe operation capability. So if we want to design a wind turbine, responsibility of finding out how much power is available at that in space or particular place. And for that, we need to find out the wind speed variation. So if you have historical data, we can actually analyze the data and find out how much power we can expect. So to do that, obviously, let us first look at the wind characteristics, how it varies in general, and then we'll see how to analyze it to estimate how much power we can actually get. So the assignment will be based on this, in fact. I think the assignments are ready for, well, we can give it maybe after a while. So this is what we will basically give you to look at and try to solve, and then we'll have a discussion, I think, not tomorrow, but day after tomorrow on that particular assignment. So in terms of the mechanics of the wind, so obviously there's a spatial variation in heat transfer to Earth's atmosphere created by variation of basically, well, creating a variation in the pressure. So there's a differential heating of the sun, the solar heating, that actually generates a transfer of heat, and that essentially causes a variation in the atmospheric pressure field, and that actually is the reason why wind goes actually from one place to another, and that's why the wind speed is varying, or generation of the wind is caused. So this is mainly attributed to this atmospheric pressure field, and there are four basic causes for the air movement from high to low pressure region. The first is the pressure force, obviously. The second one actually is due to the rotation of the Earth, and that's the Coriolis effect. Third one is inertial forces. It's large scale circular motions in a global scale. And the fourth one basically corresponds to the frictional forces. So we'll see or look at each of these. First one is the pressure force, and the pressure gradient del P del N times 1 over rho is proportional to the pressure force, so it's minus 1 over rho del P del N. So meaning that the pressure increases, force basically here will decrease, or vice versa. And the Coriolis force Fc is given by F times U, where F is the Coriolis parameter, U is the wind speed, and the Coriolis parameter is defined as 2 times omega times sine phi. Phi is the latitude, omega is the angular rotation of Earth. It's a small value, but obviously this sine phi is going to be 0 at the equator because the latitude is 0. So at equator, we don't have the Coriolis force. That's why at the equator, they say the geostropic balance breaks down. Normally, geostropic balance is the pressure, balance between the pressure force and the Coriolis force. And in equator, you don't have this force, but it's present in any other region. Now, if we look at the atmospheric boundary layer, and this is called the lapse rate, so the change in pressure is given by minus rho g dz. It's a linear variation, linear hydrostatic variation of pressure, basically. And from the first law of thermodynamics, we know that dq is du plus pdv, which is equal to dh minus v dp. And if we assume for adiabatic condition, dq will be equal to 0. So that means we can get relation between dt and dp. Now we know dp, or the lapse rate, from here, so we can substitute this here, and that actually gives a variation of dt with respect to dz. Or sorry, dt with respect to dz. And the terms here correspond to U is the internal energy, E is the enthalpy, mu is the specific heat, and Cp is the constant pressure specific heat. So this is again from your first or second year thermodynamics. So as I said, if you have an adiabatic condition, then you have Cp dt is 1 over rho dp, and obviously we can write dp as minus rho g dz, and if you substitute, then we have Cp dt equal to minus g dz. So which gives dt dz adiabatic is equal to this particular value, which is 0.0098 Kelvin per meter. So there is a drop of 1 degree every 100 meters or so, roughly speaking. This multiply this by 100, it's going to be 912.98, close to 1. And 1 Kelvin, obviously 1 degree centigrade. So minus 1 degree centigrade every meter. So that is actually change in the temperature. And this is important for atmospheric stability and the generation of turbulence. Because as I said, in the wind, we have a laminar mean profile, but also we have a turbulence. So obviously we have to account for this. So I didn't discuss about the other two terms like the frictional forces and the large scale motions, because if you're talking about wind turbines, they're only local to a particular situation. And therefore, the inertial forces are not that significant unless you're looking at a large scale weather prediction system. So the atmospheric pressure obviously is very important. We also have a variation of the temperature. We have the Coriolis force if you're not near the equator. Viscosity, viscous forces. Viscous forces are important when you're near the boundary. So there is actually a theory which is based on taking the boundary into account, and that particular theory does account for the equations of motion and the effect of viscosity. But normally we do not account for that in terms of the wind speed prediction. Based on what we're doing, it's called the empirical method of prediction. But if you're using the mechanics equations like the Navier Stokes, then you could actually use theories where we solve the equations. In that case, if you do take into account the boundary, then we know that the shear is actually important at the boundary. So in terms of the variation in time, normally there is actually 1 year variation. It's a long-term prediction, and for that we use a 30-year data. So if you have a 30-year data, we take the annual average over last 5 years, and for any inter-annual variation, which is of the order of 1 year or longer, we can actually then calculate long-term mean and how it changes with time. And then based on that, obviously we can do some statistical calculation and prediction at 90% confidence level is what we use. So this is the inter-annual. Annual variations are possible because of the significant amount of seasonal variations. So every month there is a change. So you can actually get the monthly wind speed and see this variation. So first is the yearly one. And for that, you take a long-term data, take the 5-year average, then slide it over a period to see how it actually varies yearly. The next one is every month, how it's changing. Also, you have a diurnal variation, which is at a daily scale, which is the differential heating of the Earth's surface. That means between day and night. So over a 24-hour, you might take an hourly average and see how it's varying. And then that gives you the variation. And then if you plot a typical wind speed, this has actually the mean, but also the turbulent part, which is the random high frequency part. And the mean is actually this varying part. And this mean also has all the 3 elements I said, the interannual, annual, cyclical variation. So this is day and night variation going on. But then we have high frequency oscillations even within 1 hour actually. And not significant, but maybe just by a degree or 2. So even within, say, morning 9 a.m. and 12 a.m., you might actually, morning 9 a.m. and 12 noon, you might see variations of 1 or 2 degrees actually. So we would like to model this and the mean wind speed and the turbulent component separately. And to do that, obviously, first of all, let's look at the profile and obviously look at the short-term prediction of wind. So this is actually the forecasting part. And there are various ways to forecast, and this is basically what we're doing is sort of a time series prediction here. So in terms of additional effect, in terms of turbulence and gust, obviously turbulence will have to be characterized by some spectra. We'll look into that. And the gust, which is more of a deterministic phenomenon, can be modeled by a time signature. Again, we'll see how we do that. Usually the mean variation over 10 minutes is taken. When we say the mean, means a 10 minutes average, and sampled at 1 second or less, typical. The stochastic character is represented by the turbulent part, and the gust, as I said, is a discrete unit. So to estimate the potential wind resource, we take the mean flow of air, which is dm dt, to a rotor disk of area A. So now what we're doing is we are approximating the wind turbine by a rotor of area A. So instead of 3 blades, we are saying that my wind turbine is now a blade, sorry, a disk of rotor A of area A, which is pi r, say r squared, where r is the radius of this wind turbine. So if the amount of mass flowing per unit time is dm dt, then obviously we can say that that is represented by rho density multiplied by area A times velocity u. So this gives you the mass rate of flow, because A times u gives you the area flow times the density gives you the volume flow, and to the multiplied by rho you get the mass flow. Density is this value, u is the velocity of the wind. So if you take this and then you want to find out the equivalent kinetic energy, then that gives you the power within the wind that's flowing. So it's half dm dt times u squared, which is equal to half rho a u cubed. So this is basically the flow rate here, and we know that kinetic energy is half mu squared, and if you take the time rate of energy, you get the power. So this is essentially the power. And you can see that now power is proportional to cube of the velocity. And I think we're discussing this in the morning as well. So power is proportional to the cube of the velocity. Power is also proportional to the area, which is basically the square of the radius. And power is proportional to the density, or density to the power 1. Sometimes it's called 1, 2, 3 law, because it's proportional to density, proportional to the square of the rotor radius or diameter, and proportional to the cube of the velocity. So that's why if you grow taller, that's why the aim has been, or the trend has been, to build taller wind turbines, because as you grow higher up, your wind speed increases. And that means if you double your wind speed, your power generation is increased by 8 times effectively. So enormous benefit you have going higher. That's why somebody was asking, like, vertical axis wind turbine actually doesn't score much here, because the height is starting from bottom to the level where you have the vertical axis. But you can put all the blades at a higher height, then you have a significant advantage. The interesting thing also to point out is that the type water has a density of 1,000 times the air. So if you put the turbine underwater in a tidal turbine, you get a huge amount of benefit in terms of power generated, because it's 1,000 times. Problem is more significant. If you think that, and we're discussing this, that aerodynamics is a complicated thing, hydrodynamics is still far beyond reach. And how flow occurs, including what we call is stall here, and we haven't talked about stagnation points yet here. But in hydrodynamics, there's something called stagnation points. And if there are stagnation points present, how to deal with those situations theoretically is still not known. And tidal turbines are sometimes subjected to stagnation effects as well. And that might also cause a lot of wear and tear, including damage to the turbine, debris, and other things. And in fact, in a very recent work, we haven't published it yet, but we've sent to Journal of Fluid Mechanics, JFM. We have very recently shown that you can have sub-atmospheric pressure, which is counterintuitive. Because in a body of fluid, normally you expect that pressure increases as you go inside the fluid, because the weight of the fluid is active. But we found that in a case where you have something like this, you might actually also get negative pressure. Negative meaning that sub-atmospheric pressure. So this is something that is not very well understood. So this also is very important to note that while we can actually increase the height and gain in terms of power generation, but also we can increase the diameter. So we can build larger wind turbines and also have benefit there. By increasing the rotor diameter by twice, you get 4 times increase in power. So think about, this morning I was showing how the wind turbines are growing. I told about this 30 meter, 40 meter, and then I said the rotor diameter is 126 meter. Now it's 160 meters. So 160 divided 2, which is say 1.4, roughly speaking, and square it, it's 1.4 is root 2, so twice. So by changing, or by being able to build a wind turbine of rotor diameter 160 from 120, simply by doing that, you've been able to increase the generation capacity by twice. So in fact, the current trend is to see how we can actually use the air flow in the lower range, below 5-6 meter, and generate more power rather than going on the higher side. Because we have seen from the power curve that beyond 17-18 basically to stop the operation. And some machines and some turbines can now operate even beyond 20 meters, like storm control or something they call. But really, we can't generate power beyond that yet. In fact, in a lot of places, you'll find that the wind speed is greater than 20 meters. I mean, 15, 16 meter wind speed is not unusual to have. Within campus, if you do some measurements, very easily get 10, 12 meters per second at the top of the building. So in most cases, it's not that the resource is not there, but we can't actually tap to those resources. So if you know the power, then what is important is the power density. And obviously, you divide the power by area to get the power density, which is half rho U cubed. Now, if you take a horizontal axis wind turbine, approximately 45% of the power is harvested by this HAWT. So this is the power that's generated, this is the power that's available in the wind. Now, not all of this power can be actually extracted out, and there's a theoretical limit called Bates limit, we'll see. But typically, about 45% can be harvested. And if you have an average wind speed density based on hourly average, so this is for the instantaneous wind speed. So then you can actually calculate the average power density. And for that, you need to take the average of U cubed. And the way it's done is normally we take the instantaneous input value for a number of different measurements. And then we use a factor called KE, which is the energy pattern factor. It tells us how the energy is varying over a certain duration. And KE is obtained by using this expression. So basically, it's the average value of UI cubed. And this is basically the sample value at n different moment in time. And if you have a year's data available to you, hourly average for the year, we know that there's 8,760 hours in a year. So obviously, you have 8,760 data point. And from there, you can calculate the energy pattern and then use that to calculate the average power. So if you do that and find out that if you have less than 100 watt per meter square, it's foresight actually. It's 400, then it's good, and it's over 400, then obviously it's a site where you can actually exploit wind energy sustainably. So if you want to install something, you can do this calculation. So exercise will give you something like this. So you can do something and find out whether it's possible to generate power. We also discussed about the variation of wind speed with height. And one such variation is expressed by something called a log law. So wind speed uz at height z is given by logarithmic value of z over z0. Z0 is the surface roughness, and z is the point where we want the wind velocity. U star is the friction velocity. K, or you can actually write it in this form. You take the expression here and you can rewrite this in this form, and this will give you the value of the velocity corresponding to an elevation of z. We can write this in a slightly different form where we can eliminate the factor u star and k because they're two universal constants. We may not know exactly what the friction velocity might be, but what we could do is if we have measurement at two different locations, say for example, this is surface roughness z0, function of terrain, and if we know what the velocity actually a way to find out what the velocity profile might be. An alternative form is given by power law, and this is actually given in the IEC 6400 code, as I said. And this is the International Electrotechnical Committee code for wind turbines, actually. And they have all the details I'm discussing are available in some form there. So this is power law. So you do the same thing, except that now you have an exponent alpha. And this alpha is a function of elevation, time of the day, season, terrain, and temperature. And this is actually expressed by this given expression here. And U ref is the velocity corresponding to reference height of Z ref, and the surface roughness Z0 is given here. So you can also calculate alpha depending on what the surface roughness is. So based on this, we can do the calculation, get the alpha value, and use this expression again to get the profile of the velocity along the height or along the elevation. So this gives the velocity profile along the elevation. So that means we know the velocity at a particular point. And obviously, to this we have to add the corresponding turbulent factor. Now, for these profiles, obviously, we'll be using some parameters, and that will be given by certain reference values as well. So, but if we have, say, data, we might be able to get some information about the velocity at a particular point, at a particular site. So, the next thing is then to see how we can actually analyze the turbulence. Now, normally the turbulence intensity is defined as the expression is given here, but I think it's the next slide. But the velocity is given by the mean value plus the fluctuating component. The mean value is obtained by averaging the velocity over 10 minutes. We've seen previously. In a sample form, you can write it like this, where delta t is the sampling time, so it's the same thing, but just in a discrete form. And yes, so as I said, the turbulence intensity is defined by the sigma u divided by the mean value of u. Sorry, there is a typo here again. I think this should be u bar, or let me check. No, sorry. So here the mean value is capital U. So this should be capital U. Let me just make a small change here. So the standard deviation can be computed like this. So you take the sample value and take the difference from the mean value. Again, this is capital U. And the mean value has been computed based on the 10-minute average, the data. So you get the variance, and that gives you the turbulence intensity. And normally, turbulence intensity varies between 0.1 to 0.4, depending on the site features and surface conditions. Again, code prescribes some turbulence intensity for various conditions and various load tests as well. So you can use those. Now, this turbulent part obviously is random in nature. So we can have a probability distribution of that in terms of its description. And normally, if you use a Gaussian description, then this is what you have of the wind velocity given by the mean u, and sigma u is the variance. Now, you can see that we have a mean value here, but this doesn't actually ensure that we'll all have values always positive, because if you look at the probability distribution of Gaussian distribution like this, then it's possible that you can have negative values here. And obviously you have positive values, but obviously it's relatively less possible if you have a large mean value. So depending upon what the mean value is, you can have a positive or a negative value, but that's okay, because here we are modeling the total wind speed distribution, because it has a random fluctuation. So you can have mean minus that random fluctuation, giving eventually a negative value. So you can have a positive or negative value. Now, in terms of finding the statistical structure, so that's the distribution based on Gaussian distribution. You can also have, and that's normally done, is an autocorrelation function. So what we do is now we take two time instants. One is I, and the other one is I plus R, where the time lag is given by R times delta t. Delta t is the sampling time. And we take the correlation between the two. So take the product, and then over a window of, say, this is I, so I minus 1 to ns minus R. So obviously, this is a window we're taking, and over that, we are taking the average of this product. divided by the, not really the average, divided by the variance square for the same window. And bear in mind here what we're doing is we are taking two different wind speeds which are apart by r. This is I and this is I plus r. So this is actually the time lag. So this is actually what is called a lagged correlation. And r is the lag number. Now this r we'll see is related to the integral time scale. And a time scale essentially connects to a frequency in the frequency domain. And if you know the frequency, essentially that is corresponding to your turbulent structure, in fact. But let's see what it gives. So if you look at the next slide, then this is the autocorrelation that we have completed, and let's plot it. When we have lag value of r equal to 0, obviously we should have a value of 1, because if you go back here, and if you put r equal to 0, this is ui square. Sum of ui square is nothing but this is basically your variance. So if you take the average of ui square divided by the variance, you get a value of 1. So we have a value of 1 here. If the two particles are very far apart, you basically expect that there will be no correlation. And therefore, when this curve eventually crosses the 0 line, that actually gives you the corresponding time separation distance between two particles which are almost uncorrelated or not correlated at all. So that means if you take two values, those two values are not correlated at all. So now let me just draw another diagram here. So let's think of a flow structure where we have some turbulence, and let's say turbulence essentially is represented by some vortex and vorticities. So you have some circular structures like this. So within this circular structure, there is a circulation taking place, meaning that the flow is kind of connected to each other. So obviously, if I take two values which are somewhere here and here, or within this field somehow, there will be some correlation between the two. And if I take two values which are absolutely at the same position, then I have a value of 1 because it's perfectly correlated. And these 2 points are kind of at the two extremities. And once we go beyond this, like outside this structure, then there's not much of correlation because it's not in the same kind of circular motion or eddy. So effectively that time length where we have 0 correlation corresponds to, in a spatial scale, this distance, or in terms of the length scale of the eddy. So this is actually your length scale of the eddy. So if I take that time and if I can convert that to an equivalent length scale by taking some velocity, okay, then the length scale will correspond to the length scale of this turbulent structure. Now, naturally, the velocity that we can consider here is the velocity of the wind that's propagating. So we assume that whatever is the wind that's blowing is effectively responsible for this creation of the structures here. And therefore, from here to here, obviously it's moving with a speed which is equal to the mean wind speed, because the mean contains everything sort of averaged out. So if I take the mean wind speed and multiply by the integral time scale, then essentially we get a length scale which is corresponding to the length scale of the eddy. So that's why this expression of integral length scale is equal to integral time scale multiplied by mean velocity. And to get that, if you have the wind data, and if you do an integral autocorrelation from zero lag to first crossing, that gives us the integral time scale. And if you know the integral time scale, and then the length scale essentially, then we can use von Karman's model for turbulence, which is given by this expression here. And you can see that this is the variance of the wind speed, which we have computed from the data. The length scale has been now obtained based on the autocorrelation analysis. U is the mean wind speed, we know what it is. F is the frequency, and basically this is the function which tells us how the energy is distributed over various frequencies. So this is the turbulence structure. So given a wind data, you can do the analysis and find out the corresponding turbulence spectra from the data. It's interesting to point out that if you look at this structure, you have a power of 5/6. And you have a square term here. So if you multiply it with 2, you have 5/3. And because you're in the denominator, take it the numerator, you have minus 5/3. So this is basically following the Kolmogorov's minus 5/3 decay of turbulence. As you know that if you look at the scales of decay, Kolmogorov did a dimensional analysis of the Navier-Stokes equation, and he showed that for the turbulence energy spectra, obviously it's something like this, but this decay is actually of the order of minus 5/3. So this is how the energy is distributed or gets dissipated. What happens is that larger eddies, they break down into smaller ones and transfer the energy. And then as we go, because if you have a large scale eddy, viscosity of bulk dissipation is not actually very high, but the molecular viscosity is very high. So energy dissipation takes place at high frequencies relatively. So when the big ones break down and cascade to smaller ones, effectively, energy is transferred from low to high frequencies, and then at higher frequencies, obviously, it dissipates. So this is where the viscous terms dominates. This is where the inertial terms dominate. So this is the inertial rate, this is the viscous rate. This is how the dissipation takes place. And this is exactly what we're doing. So now if I give you a data, you'll be able to analyze the data, get the distribution, the Gaussian distribution. You should be able to also find out the mean and the variance, also plot the autocorrelation, get the power spectral density function. And then once you have that, obviously you know the 10-minute average, you know also the, if you have the annual variation, then you can get the intra-annual, monthly variation, daily variation, and then mean in terms of the short-term prediction, you should be able to get the 10-minute average, and then from there, by generating the turbulence spectra, you should be able to generate the random process from there, by taking the inverse Fourier transform, or you basically sum up sines and cosines with certain phases, and then add that to your mean value of the wind. That generates the random wind fluctuation. Now, that is for a particular point or location in height. You also know the power law, so now you can also generate how the wind time histories are going to vary along the height. Okay. So this is how you can generate the time history of time analysis. You can also look at the site and generate the power based on the data and decide what is the power that can be generated from the wind, and based on that recommend what sort of turbine can be actually installed, or what kind of, or what rating of the turbine should be then installed. So all these things can be done based on what I've discussed so far.
And question, you draw the eddy current, is it around the cross section of the wind, or is it like separate current evaluation.
Yeah. So this is in a 2D framework I've drawn. So it's essentially planar. So in plane, and so all I'm saying is that if you have two particles within the same eddy, they will be correlated. If they're outside, then there is no correlation. Therefore, the point corresponding to the zero autocorrelation in time is actually equivalent to the length scale of the eddy. And how do I get that? I'm saying that I'm just using some velocity. I have to use the velocity. And I'm saying that because the propagation is taking place in terms of the mean wind speed, which is sort of the average one, it's not technically accurate. But if I multiply the wind speed, or mean wind speed, with that time scale, which I've got from autocorrelation, that should give me the length scale of the eddy.
But it's not rotating over the blade. It's just you saying the concept of the general air.
Yeah, because at the moment when you're doing the analysis, there's no wind turbine actually. You're just getting the site data. So if the wind turbine is there, then you have to use a concept called the frozen. And I showed you some simulations in the morning. You know, in the plane, there was some eddies generated and so on. And then I said that you can transport that onto the wind turbine plane, rotor plane, by using certain transformations, so that you have the velocity here, and then you bring it to the wind turbine. So essentially, it's called the frozen rotor turbulence because it means that whatever turbulence is generated here, you just take the whole thing and transfer it on the wind turbine plane. But
so for each cross section, it will be different.
Yeah.
So in the morning you showed
several cross sections.
Yeah, several cross sections. So when you study all of the blade, you have to check each cross section and analyze whether each point has correlation or just one plane you take.
So this is for a particular point. So this is for a particular point in the plane.
Okay.
So in the spatial domain, there's also a correlation.
Yes.
So this is only in the time we are talking about. So that spatial correlation, which is called a coherence function, will also have to be added to generate what I generated.
Yeah, but the time was won't be there between the planets, right? The correlation.
No. You can also use this rapid distortion theory, but that's a different theory altogether. It's by Townsend. Townsend actually did this analysis where, so here we are not satisfying the equations of motion. So this is basically empirically generated, meaning that we are not satisfying the continuity equation, we are not satisfying the momentum equation. But in rapid distortion theory, you can assume your 3D flow field and you can solve your Navier-Stokes with certain assumptions and approximations. And then look at the stochastic variations of the wind field with certain boundary conditions. So that's another possibility. But then we are going to quite deep and advanced topics now. You can have a full one course on just Navier-Stokes, or even like on this sort of numerical integrations of these type of nonlinear equations. So a full course on what's called the nonlinear Schrodinger equation or something. And a full course on dispersive and dissipative systems. So these are topics by itself actually. But let's simplify. Let's see what we can do. I mean, you can still do a lot of things with this. But as I said, like you can do a site assessment, you can find out what the capacity or what the wind resource is there, and then decide what capacity of wind turbine you can install. You can also generate wind speed variation, you can also generate the turbulence, you can add the two, you can also simulate time domain signatures for time, wind speed time space. We'll also look into things like rotational sample spectra. I'm not going to the detail right now, but this spectra I've shown is not valid for use on the rotor plane. And because of the rotation of the blade will sample this turbulence periodically. And therefore, the turbulence spectra will get modified with peaks at capital omega, 2 omega, 3 omega, and so on. And what happens? Energy from part of this here goes here, here. This is your omega, omega. So, in fact, sometimes it is known that this is called a 3P effect. It becomes quite dominant, and they can couple with other structural systems like the blade and turbine. And more recently, people have seen that this may actually influence the design of the foundation. Previously, like all the wind turbine manufacturers and operators, they used to design the turbine, and the foundation used to be designed by geotechnical firms and engineers locally. Very recently, I think they have now realized that the design cannot be done separately, and I think they are now prescribing how to design the foundations, because all those frequencies then will be transmitted to the foundations. And therefore, design of wind turbine foundation is not like designing the foundation of a bridge or a building. It's very different. So, but anyway, that is very important also for blade design and so on. But this is something called a rotational sample turbulence. So this is what you see on the rotor plane. But if the wind, but this is the discussion going on in the context of a particular site where you don't have any wind turbines. So we don't have that here right now. The cast obviously is a special signature. I think we have actually gone past 5:30 already. Should I continue? Is that okay? Let me check the slides. There's quite a few, but let me at least go to a stage where I can stop. Then at least a few I can cover tomorrow. But this is the signature of the gust. And you can see what happens is that there's an initial drop in the wind speed, and then the speed again recovers and goes up to a certain value. This is the peak here. The first trough is here, and then it falls again. And in fact, the second trough is at a lower value than the first one, and then goes back to the original. There's a very special type of signature, and this is what happens when a gust is there. So before the gust arrives, there is actually a decrease in wind speed, and then there's a sudden increase, a sharp increase like this, and then again a sharp drop, and then again going back to the original. This basically is representative of gusts, and the amplitude is A. B is called the rise time. D is called the lapse time, and actually there is again a typo here. Is corrected. So C should be the maximum gust variation. So this should be C. Apologies. So now how to forecast the wind speed? Basically, this is what I've just now mentioned to you. So you take the data by using the direct views of the data. We take a long-term average based on n sample observations. And this could be like if you have data for 1 year, you take the average for 1 hour. So you have 8760 samples. So then you have those means, 8760 means, and then you can take an average of that. You take a standard deviation. And from there, you can actually get the average wind power density based on this expression, which we have discussed obviously. Next, we can also compute the energy density per area. So simply taking half rho summation of EI cubed, which is given by this value here. Now, this actually has to be translated to the average machine wind power. But for that, you need the power curve, because given the wind velocity, you need to know how much power is generated. Now, this can be either given by the manufacturer, or can be experimentally obtained, or you can simply use a power curve based on the calculation of the power. Like I said, power is given by half rho A U cubed. So you can use that to generate with a certain efficiency factor, and you can use that as 0.45. As I said, most cases get 40-45%. And then from there, you can also get the energy because multiply power by time. That's basically the energy. And once you have this, then I think the previous expressions were given to you to see how we can actually write the expressions in discrete form. Now what we're doing is, say, if you have real data, then it may so happen that one particular velocity might have actually happened more than one time. So if you have that, say, n number of times, then there's a frequency of occurrence of these velocities. So appropriately, then you put those in a certain bin with certain weight of wj. So that means you take a velocity between, say, v1 and v2, and you see number of times the velocity has been in that region, and then you multiply it by the mean by the number of times. So just sort of frequency analysis, and so it's the same expression but just in a different form. And the same for the variance and the power and the energy. So it's pretty much the same, but just in a more statistical formal way of doing it, but nothing much. Now, after you've done all that, here comes the trick actually. So we know that the wind speed, mean wind speed, is also a stochastic quantity. So you have taken it from a data which is sampled and observed, but that doesn't mean that last year what happened will happen this year as well. So there is a stochastic variation. And the mean speed, we saw the total wind speed variation is a Gaussian in nature. But if you take the mean wind speed only, then the variation of that is described by a probability density function, like a Rayleigh one. And the reason is because you see, wind speed, mean wind speed is always positive. So you can't have a negative value. So obviously Rayleigh describes it very well. And these are the probability density function curves. This is the distribution function. And if you look at this, what is the unknown parameter here, which is basically U bar, which is the mean of this. So if you calculate the mean from the data that you have from last year and put it in this expression, then you'll be able to get the probability density function corresponding to the site. Okay. So from the site, obviously we've analyzed the data, we know the mean speed, we've analyzed the raw data, but we now want to also get a probabilistic description of the distribution of the mean wind speed. And obviously this is going to give you that one. And because you have only one parameter, so obviously it will fit the mean, and that gives you your mean. There's also a better description, which is given by a Weibull distribution, which is given a particular data again. In the Weibull distribution, you have two parameters here. One is K, other one is C. So in the previous one, we had only one parameter, and that parameter was really the mean. In this case, you have two parameters, K and C. Now we also have mean and variance from your data analysis. So if you use the mean and variance from the data analysis and theoretically calculate the mean and variance of these distributions in terms of K and C, then we should be able to find out what the values of K and C are, right? And in fact, here you can see that if you know the mean and the standard deviation, the K is given by this expression. So if I go back, what I did really was essentially took the mean value of this. So integral u pu du from 0 to infinity, and that gives the mean, and integral u square pu du 0 to infinity gives the variance. So if I take the mean and variance and integrate this expression, like I said, essentially I will get the two expressions giving the values of K and C in terms of mean and the standard deviation. So knowing the mean and standard deviation of the data, we'll be able to get K and C, and that then gives us the distribution of the Weibull distribution. This is the gamma function here. For K equal to 2, the Weibull distribution actually gives the Rayleigh distribution. So Weibull is a more generalized distribution, let's say. And how to measure wind speeds? Obviously, there are various ways of doing that. Classically, dynamometers of different kinds have been used, and acoustic measurements have been also done. But currently, LiDAR is being used, so laser-based measurements, and what people are doing is actually upstream velocities are being measured, and then based on the analysis and forecasting, they are predicting what the wind speed going to be after a certain duration of time, and what they're doing using it for control actually, and that actually gives us information, in fact, in advance of the wind coming to the turbine, and that way we are sort of accounting for the non-causality in controlling, because we don't know what's going to happen in the future, but based on wind that's there already, I can say what's going to happen after, say, 10 seconds or half a minute. And based on that, I can react in advance of the wind coming to the wind turbine so that I can appropriately pitch my angle of attack appropriately. Because by the time the wind comes, if I pitch my angle of attack, it's too late to do that. I have to do that in advance to account for the effect. So, well, I suggest that we stop here because there's a bit of things to cover, and I won't rush through this. I mean, these are again a bit conceptual, though. Yeah, so I think it will take about 15 to 20 minutes. So, because it's approaching 6 already, maybe I'll give you a bit of time to ask questions. And I think what I've given you is good enough for you to try out the assignment. So the rest part won't be needed for doing the assignment. So we'll continue from here. There's about 8 or 10 slides, and this is not completely disjointed or disconnected from the aerodynamics thing we are going to discuss tomorrow. So it will be well in line with that. And today, because it was the first day, I mean, I maybe took a lot of time explaining things which are not just in the slide, but peripheral things and so on, and discussions that went on. So now that we are kind of deep into the wind turbine, we'll focus more on what's there, actually, rather than not things that's not there. Actually. Okay, so let me give you a chance to ask me questions right now for the next 5 minutes. In the what is the situation where you have the assignment sheets? Should we give the assignments to them? Yeah, because based on what I've discussed, you can start attempting the assignment.
Related to this window assignment, because we want to install a wind turbine in a particular location. If we don't have the data over there, should we wait for 2 years, or can we use the data which are available for the year?
So what you're asking is
how,
that
how close it should be. For example, we have some data at a particular location, and we don't have the exact data at that location that we would like to install that data. How close this region should be?
So I showed the mean speed variation is a function of the terrain and surface roughness and so on. So if you have a similar kind of terrain, surface roughness, you expect to have similar kind of wind profile actually. So you can use those for your calculation.
One more question related to this power wind speed plot. It's on some rated speed, rated power response to a particular velocity, 19 to 19 meter per second. So my question is some anomalies plot or what?
So it was a general plot. It was general plot, but the value of 1819 is actually quite good in the sense that whatever the turbine is, cutout speed is normally around that range, because most of the it's not really just the turbine itself, but it's really the generator which decides where your rated power would be and where your cutout speed would be. Because the problem is that if you generate more than what the generator can produce, it will burn your generator. So therefore, the generator is basically the design. Not really, because it doesn't matter. Eventually, that's what is guiding the design there. So in most cases, the cutout speed is typically 14, 15, 16, 7. Now exactly depends on That could vary, but could be 15, could be 17, but it's not going to be 20. Cutout speed would be far less than 20. In some cases, they are operating beyond 20, but I don't think they can generate, or because generator design is generator design, so they can't do much about it.
So my doubt is actually for a given wind speed, if we increase the size of the turbine, then the power generated will vary.
Yeah.
So what have you shown along y-axis is some normalized kind of value or the absolute power?
No,
because
that's what I said. The figure I showed actually is an arbitrary one, so don't worry about the power, but the shape is important. And the velocity I showed, cut-in speed is typically 4 or 5 meters per second. The radiant speed is also around that range. The cutout speed is also that. But the power values are arbitrary. In fact, that will depend on a lot of other things as well, which we'll discuss in fact. But, it's called the tip speed ratio and angle of attack and so on. So it mainly that curve depends on the shape of the airfoil. Actually, that's the guiding factor.
So I have a question related to the same, like the mean wind velocity profile. You're saying about the log below, there is a log of Z by Z0. So the reference Z0, what it should be? Is it like the previous year?
No, reference is any other particular point for which you have the velocity known. That is your reference.
Okay, so
if you know at a particular height, so what normally is done is you put an anemometer. From the anemometer data, you have the velocity, say at 20 meter height. Then you use that to see what would be at a height of 80 meter, because your hub is 80 meter. So most of the power will be generated at 80 meter height.
Yeah, but this talks about the surface roughness. Because the Z was the surface roughness.
Z0 was the surface roughness. Yeah, but that's a different one.
Yeah, but the surface roughness of the terrain, basically, right? So, which means like the more you go to the mountain regions, or is it related to something like that?
It is called orography or something.
So, more you go to this harder core places, you have more the velocity. Is that the notion or the?
Yeah, so there are classifications given in the code again. One is like completely plain terrain without any obstruction. Then the second one is where you have some obstructions. Third one is where you have very undulating terrain and a lot of obstructions and so on.
Yeah.
So that will.
So when we go to mountain regions, you have more obstructions, and the wind velocity should be destructed, right? The mean wind velocity. Or
no, I don't think that's right. It basically depends on. So if it's a green field, then it's not obstructed at all. Then you have a higher wind speed.
Yeah.
If you have an urban situation like here with a lot of buildings around, there'll be a lot of obstruction.
Yeah.
So this is one particular aspect.
Yeah, but most time the offshore, for example, prefer to have either one time you said like either at the top of the mountain or somewhere.
Because that's where you have the elevation. So if you go at the top of the mountain, that's the higher height.
So how far the
Is there any data missing there? No, I'm asking, is there any data missing there?
No. I was because the surface roughness.
Yeah.
I was wondering like because more you go out of the smooth areas like as you said the Greenland or something.
Yeah, it should increase.
Is increasing, but in logically when surface roughness is increasing, the wind should be more turbulent and should not be very smooth. But we prefer to have a wind turbulent elevation. So it's a bit contradicting, wondering why. Of course, as you said, the height is increasing and the wind velocity is increasing.
Yeah, but that's at the top of the mountain.
Yeah.
But this is, we are talking about the terrain roughness, like whether there are obstructions. Like if you have an urban setting, it's more like less wind there.
Okay.
Somebody asked me.
So how far the curve or the power versus velocity curve will change for a variable and the fixed wind speed turbines?
Yeah, so I didn't discuss about the controls at all, actually. That's in the next few slides. So obviously, yeah, you'll see controls tomorrow. Hold your excitement and suspense for tonight. Let it be like a detective story. We'll find out tomorrow.
Any more questions? Okay, then well, thank you all, and that's the end of today's session. So tomorrow we will meet as per our program and try to be here at least 15 minutes ahead because we are maintaining time strictly. The program is live streaming, so please be on time. Thank you.